Hello, and welcome back to the course Physics 123 Quantum Mechanics 1. So before we start our lesson, let's first review some of the concepts that we have discussed in the previous lessons. So we have discussed about the Schrödinger equation, which describes the time evolution of our wave function psi. So psi here are square integrable functions, and they can be found in the Hilbert space. We also have discussed about the expectation values. So for continuous variables, for instance, x, the expectation value of any function of x is just defined as this equation. So you just integrate over f of x and the probability density over x, over all possible values of x. So for this session, we will be focusing on the quantum momentum, the quantum version of momentum, and in the process, generalize the concept of expectation values. So in quantum mechanics, we usually call earlier, in our earlier lessons, we call the expectation value as the average or the mean value, but it's actually not uh, not exactly what you think. So in quantum mechanics, the expectation value or the average value is actually the average of the repeated measurements on an ensemble of identically prepared system and not on the same system. So usually in classical mechanics, if you are trying to find the average of a measurement, so you measure you measure repeatedly on the same system. But in quantum mechanics, you need to prepare identical systems such that they form a large ensemble. So you have system 1, system 2, and they're initially all identical, and you simultaneously measure you measure in each of these system, and you get their values, and then you average all their values. So that's how you do it. You do the averaging in quantum mechanics. You repeat the measurements on an ensemble of identically prepared systems. So not necessarily simultaneous measurement, but repeated measurements of identical systems. So we have mentioned before about the expectation value. So for example, for position, the expectation value position is just, we define it just initially as this, but it can actually be written like this, because we take note the absolute value of psi squared is psi star psi conjugate times itself psi. So in a more standard format of finding the expectation value, you actually sandwich your operator or your variable or your function inside psi star and psi. But essentially for position, you can do it just like this. You can take out x out of psi star and psi, because x is just a multiplication operator. So in general, the expectation value is also time dependent. So your average value will change with time in general. But there are also cases that your expectation value is time independent. But in general, it's time dependent. So for instance, if your expectation value of x, in this case its position, is time dependent, it explicitly depends on time. So meaning expectation value of x is something you see at t, a time component in your expression for the expectation value of x, then you can use the, or you can get the velocity of the expectation value dx dt, or the quantum, what we call the quantum velocity multiplied by mass, to get the expectation value of momentum. So if you will recall, momentum is just mass times velocity, mass times dx dt. So this equation is only true if your expectation value, sorry, explicitly depends on time. But if there's no time component in your expectation value, you cannot use this equation. So this is only true if your expectation value of x explicitly depends on time. So here dx dt, the time derivative of the expectation value of x or position is what we call our quantum velocity. So all classical physical quantities can actually be expressed in terms of position and momentum. So the basic quantities actually in physics are position and momentum, and other quantities can be derived as a combination of position and momentum. I think you have learned this in your classical mechanics. And one peculiar thing about expectation values is that they obey classical laws, such as like this. So this looks like a classical law, mass times velocity. So if, for instance, if you want to find the expectation value of kinetic energy, it's just the expectation value of p squared over 2m. So that looks like a classical expression, p squared over 2m. Also, if you want to find the expectation value of the force, then it's just the time derivative of the expectation value of momentum, p, dp dt, Newton's second law of motion in classical mechanics. So expectation values obey classical laws, but the x and the p themselves doesn't obey classical laws, only their expectation or average or mean values. So for any quantity, physical quantity q, which is now a function of position x and momentum p, the expectation value is given like this in general. So we have an equation before that if you want to find the expectation value of f of x, it's just f of x times the probability density. In this case, the probability density is psi star psi. So in general, if you have a quantity q, x and p, in order to solve for its average value or expectation value, you just need to sandwich it between the conjugate and the wave function psi star and psi. So sandwich, you put it in the middle. So take note that this q here is the operator form of your physical quantity q as a function of x and p. So in the case of position, for instance, the operator form is just x multiplied by x. So it's not necessary, you don't need to necessarily place x in between psi star and psi if you're just finding the expectation value of x. In the case of quantum momentum, its operator form will look like this. So it's actually a differential operator. So in one dimension, it's h bar over I partial with respect to x. So it's a differential operator. In 3 dimensions, the quantum momentum operator is h bar over I, and it becomes the gradient operator or the del operator, partial with respect to x, x hat, plus partial with respect to y, y hat, plus partial with respect to z, z hat in Cartesian coordinates. But take note that this definition of quantum momentum is only in the position space. We define momentum in the x space. Later on, we will go to the momentum space and things will change, or the definitions will change. So this is now the definition of the expectation value of quantum momentum. So you sandwich the operator form of the quantum momentum between psi star and psi. Take note that you cannot place this before psi star or say after psi, because this is a differential operator, partial with respect to x. It needs something to operate on. So meaning, from this position or from this form, your momentum operator will first act on psi, and whichever is the result of that operation on psi, you multiply it to psi star. So that's how you get the expectation value of quantum momentum. So let's just have a simple example for expectation values, since we are generalizing expectation values here. So you are to prove Ehrenfest theorem, the previous equation that I've shown you before, that the expectation value of the force is just the time derivative of the expectation value of momentum, so dp dt. So here's the proof. So this is the expectation value of momentum. So in general, if you have expectation value of q, you put the operator form of your quantity q between psi star and psi. In this case, our operator form of momentum is h bar over I, partial with respect to x. So we take out the constants, the h bar and I, and then rationalize I so that it will not be in the denominator. So you multiply by I in the denominator, you multiply by I in the numerator, so you will have I squared in the denominator, that is negative 1. So you have negative I h bar. So you take out all the constants, and what's left in the integral, inside the integral, will be psi star and partial of psi, derivative of psi with respect to x dx. Okay. So since we are to prove Ehrenfest theorem, so we take the derivative of this with respect to time. So meaning, we take the derivative of this integral with respect to time. And again, differentiation and integration can be interchanged. Instead of differentiating with respect to time first and then, instead of integrating first and then differentiating with respect to time, we can actually differentiate first and then integrate after. So when you place the total derivative inside the integral, it now becomes a partial derivative. Take note that this integral is over dx, which means if you integrate over x, you will no longer have an x variable, and the result of this integral will be, say, time dependent. So that's why it's just a total derivative of time. But if you place it inside the integral, so your size here are functions of two variables, x and t. So it now becomes a partial derivative with respect to time. So we need to take the partial derivative of this, of the integrand, which is psi star partial of psi with respect to x. So the key here is to solve for this term inside the integral. And how do we do it? So we first focus on this integrand here. So the partial derivative of this with respect to time, since this is a product, then the derivative of products is just, so psi star times partial with respect to t of this one, partial of psi with respect to x. Again, when you are differentiating with respect to two variables, such as in the case here, that this is we first differentiate with respect to x, and then we apply differentiation with respect to t, you can actually interchange the differentiation order. You can differentiate with respect to t first and then differentiate with respect to x later. So that's actually what we did here. For the second term, so this, since it's a product, the derivative of f and g is just f derivative of g plus derivative of f and g. So our g here is partial of psi with respect to x. So partial of psi star with respect to t. Okay, how do we get this partial of psi with respect to t and partial of psi star with respect to t? So of course we go back to our Schrödinger equation. So from our Schrödinger equation, we have IH bar partial of psi with respect to t is equal to negative h bar squared over 2m partial squared of psi with respect to x squared plus u of psi. So that we can get partial of psi with respect to t, which is just this term that we need here. So we divide both sides by IH bar so that we are left with partial of psi with respect to t. So divide by IH bar, so or actually multiply by negative I, so that negative I times, we will actually multiply both sides by negative I over h bar, negative I over h bar, so that the h bar will cancel and negative I times I is negative I squared, and that will give you positive 1. and you will get negative I, negative 1, so you positive I h bar squared over 2m partial squared of psi. Sorry, there's an h bar here, so this should be just h bar respect to x squared, then minus I over h bar u of psi. This is our derivative of psi with respect to time, the term that we need here, partial of psi with respect to t. So we will also need this term here, partial of psi conjugate with respect to t. And since we already know partial of psi with respect to t, then partial of psi conjugate with respect to t is just the conjugate of this expression here. So the conjugate of this expression here is I just becomes negative I. So negative I h bar over 2m partial squared of psi with respect to x squared. So negative I becomes positive I. So plus I over h bar u of psi. So that one. So we substitute partial of psi with respect to t here, and we substitute partial of psi conjugate with respect to t here, and doing so will give us this result. So since we now know the evaluation of this expression, which is just the integrand of this integral, we plug in this back. So we replace the integrand here with this one. So there's a constant h bar, the h bar will cancel out, there's a negative I, there's a negative I, so that's positive I squared, or negative 1, and dp dt will just be equal to like this. So there's a negative 1, so there's a negative, and partial of u with respect to x inside the integral. So you will have psi star partial of u with respect to times psi, and then there's a negative 1 due to the negative I h bar times negative I over h bar. So you just group all of the terms, the negative and the partial of u with respect to x, and this will now look like as a new operator. It's like a definition of a new expectation value, an expectation value of an operator, where this operator, negative partial of u with respect to x. So basically this one, it's just the expectation value of this operator, negative partial of u with respect to x. So this is our definition of expectation value, right? You sandwich the operator form between psi star and psi. So this is the expectation value of this operator, negative partial of u with respect to x. And what is negative partial of u with respect to x? So if you write this operator in 3 dimensions, similar with the momentum operator in 3 dimensions, that operator will actually translate into negative gradient of u in 3 dimensions. And what is negative gradient of u? Negative gradient of potential energy. So that is just the definition of force. So force is the negative gradient of potential energy. So if you have gravitational potential energy, for instance, gravitational potential energy has a gradient of directed upwards, because gravitational potential energy increases as you go up or go higher. So therefore, the gravitational force or weight, or the force due to gravity, is the negative gradient. So if the gradient of gravitational potential energy is up, then therefore the negative gradient is down. So therefore the weight or the force due to gravity is directed downwards. So in general, force is the negative gradient of potential energy. So electric force is the negative gradient of electric potential energy. Gravitational force is the negative gradient of gravitational potential energy. Elastic force is the negative gradient of elastic potential energy. So there are many types of potential energies. So in this case, this is a generic scenario. Therefore, we have proven Ehrenfest theorem that the time derivative of the expectation of value of momentum is just the expectation value of the force. So that's the end of this lesson. So we will have an example of a calculation of the expectation value of momentum in our last topic for this chapter, which is on the uncertainty principle. So in that topic, we will be calculating expectation value of x, expectation value of x squared, expectation value of momentum p, and expectation value of p squared, and relate those expectation values to the uncertainty principle. So that's it for today, and thank you for listening. So I will see you next session.